algebraically. This is actually my favorite way to find limits is algebraically, and we can find the exact limits using algebra. Yesterday we found limits mostly using what? Graphing. Okay, and then the day before that we used tables. Okay, and now I'm going to show you how you can use algebra. So I asked you to write down from your textbook some of those laws, because the first thing that we're going to be doing is writing down justifications for how you can break up functions just to make taking the limit of those functions simpler. So we're going to look at our limit laws together real quick. Okay, so it says suppose that C is a constant and that the following limits exist. So the limit as x goes to a of f of x and the limit of x goes to a of g of x. Okay, now notice that with both of them, it's the limit is x goes to a, which just means you're going to be doing the limit and it's going to what? If it's a, that just represents what? Any number. So they just have to be going towards the same number. Okay, so both functions would have to be going towards the same value a. So if you have two functions added together, then you can split it up and do the limit of the first function and add that to the limit of the second function. Same thing with subtraction. If you're subtracting two functions, you can take the limit of each one separately and subtract. Now C is going to be what kind of value? A constant. So if you have a constant multiplied by a function, you can actually bring that out in front and then multiply after you take the limit. If you do have two of them multiply together, you can take the limit of each one separately and multiply. And same thing with division. Now there is a limit, or I shouldn't say limit. There is a restriction on taking the limit of division. And that's because when you're dividing, what's going to produce an error or an undefined? Yeah, 0 in the denominator, right? So if the limit as g of x approaches a is 0, then you can't use the limit of a quotient. We do have other ways that you can find it. You just would not be able to use that rule. And then we also have some special limit laws that are already on your sheet for you. So we're going to talk about those as well. Okay, so some special limits. The first one, if you are just trying to find the limit of a constant, then it's going to be equal to that constant value. Let's think about why that works, right? If it's a constant value, Nathaniel, what does the graph look like?
It's just a line.
Yeah, it's just a horizontal line, right? So if it's just a horizontal line, it doesn't matter what value that you are taking the limit at, you're always going to end up at the same y value, okay? For the second one, that's what type of function, if it's just x. If it's just x, it's what type of function? Logan, what do you think?
What?
If your equation is just x, what type of function is that? If you have y, if you just have y equals x, it's what?
Oh, it's just going to be linear, right?
Yeah, it's just going to be linear. Okay? So if you have a linear function, if you plug in a, think about if it's 1. Okay? If you plug in 1 for x, what do you get out? 1. Okay? So your variable here, whatever you plug in, you're going to get out the same thing. Your slope is 1 with this, and your y-intercept is going to be at 0, 0. Notice here, the difference between special number 2 and special number 3 is these are just being raised to a power. So if it's x to a certain variable, that's going to equal a to that same value, okay, whether it's a variable or a number. And this is going to be a positive integer for this. Okay, and then the last one is going to be the root. The nth root of x is the limit as x goes to a of the nth root of x is going to equal the nth root of a, which actually kind of stems from step 3, because what's the relationship between the root and exponents? Did you remember what that is?
Isn't it like make it to a fraction?
Yeah, you can write the root as a power if you turn it into a rational exponent. So this would be like x to the 1 over n. Okay, so it is really the same thing as 3, except now we're putting it in the radical notation. Alright, so how are we going to use these? Well, for example 1, it says to evaluate the limit and justify each step. So if the directions say to justify each step, that's when you're going to indicate the appropriate limit laws. Okay? So I want you to think about, I'm going to give you a few seconds to think about the first way that you would separate this function using your limit laws. Okay, do you guys have any ideas? Are you going to separate this?
Don't you have to factor it?
That. Oh, you could. That's actually a possibility. You could. And you could make it into the multiplication. What symbol do we have in between these? Yeah, we have plus or minus. So then can I write this as the limit as x approaches negative 2 of 6x squared minus the limit as x goes to negative 2 of 3x plus the limit as x goes to negative 2 of 1. Okay, so I can take all of those functions and then I can separate them. Notice that you do have to take the limit at each step. Okay, so Lydia, what rule did I use for that one?
Limit of the sum and limit of the difference.
Good, okay, so for the justification, you can do the difference and the sum together. So we're just going to say the limits of a difference and sum. Okay, so first we use the difference and then we use the sum. Okay, so now we want to think about, alright, is there any way I can split this apart again? So these two objects are being multiplied together. So we have 6 times x squared. What multiplication property is that going to be? Because we have 2 of them, right? Yeah, Bruno, what are our 2 options for multiplying? Okay, so using your laws, right? What are the names of the 2 laws that are going to use multiplication? Okay, so limit of a product's one. What's the other one? Yeah, limit of a constant multiple. So if it's 6 times x squared, Lauren, what do you think? Is that the limit of a product or the limit of a constant multiple? Yeah, that's right. Okay, why is it a constant multiple?
Times by 6.
Okay, so you're multiplying by 6, and 6 is a constant. Okay, so 6 is a constant. It would be the product if you had 2 functions. So like x times x squared, square root of x times x. Okay, so for the next one, let's look at our law. So our law says that you can put c, the constant multiple, on the outside, and then still take the limit as x approaches negative 2 of x squared minus, do I have a constant multiple here with 3 and x?
Yes.
Yes. Okay, so then the 3 is going to go on the outside. Okay, and this is already just a constant, so we can go ahead and leave that. So then we've already talked about this is going to be the limit of a constant multiple. Okay, now what we're going to do is use some special limits. Okay, so we are going to use some special limits here. If you have a limit of something that is squared, let's look back up at our special limits. Okay, so see how with this one we have x to a certain power?
Yes.
Alright, this is going to be the same thing, where you have x to the power of, what's our power for
2.
this? Thank you. Okay, so x to the power of 2. So we're going to rewrite it the same way. When you're taking the limit here, what you can do is you can actually plug in your a value. So see how this is x to the n? X is going to a, and now it's a to the n. What you're doing is you're substituting a in for x. So this is going to be 6, and then negative 2 squared. And that's how you would use your special limit. Okay, so because it's x is going to a, okay, your a value in this case is negative 2. So you are going to replace x with negative 2. For our next one, we have the limit as x goes to negative 2 of x. Alright, Allie, what special limit is that going to be when we have the limit as x goes to a value of x? So it's going to be another special one. Anybody help me out? Yeah, it's going to be number 2. See how here it's the limit of just x. It's the linear function we were talking about. So what we can do is keep the 3 on the outside, and then we're going to substitute negative 2 in for x. And then, Sydney, the last one is going to be what special limit? Yeah, number 1, because number 1 is the constant. So that says that you would just have the constant. And that actually makes a lot of sense, because if I were to plug negative 2 into the equation, is there any place for me to plug in negative 2? No. Okay, so for this one, we use special limits 1, 2, and 3. Okay, and then I'm just going to write down here how we used them. So this here is going to be special limit number 3. Okay, so that's L, I put SL number 3. Okay, to go from this to this. Here, this is special limit number 2. That's our linear. Okay, and then this is going to be special limit number 1. Okay, you would not have to write that down when you're writing it out. I just wrote it there for you, so if you're looking back, you're like, how do we get those? That's where it's going to come from. Okay, and then now we can just evaluate. So this would be 6 times 4 plus 6 plus 1. And these are evaluations. You're not doing the limit laws anymore. So your limit is going to be 31. So when you're evaluating, you don't have to justify those final steps there. Okay, what questions do you guys have for me on those? Okay, so when you're justifying, you're basically just telling me how you split up your limit and what you use to do it. Okay, so you'll have a few of those. Now, a lot of times when you are trying to find what your limit is and you have a polynomial, you can use something that's called direct substitution, which you guys are really going to like. Okay, so when you have direct substitution, that's going to occur when your function is a polynomial or a rational function. What's a rational function again? Yeah, so a rational function is just going to be a fraction, and you will have a function in the denominator. So it has to be a polynomial or a rational function, and it says that your a value is in the domain of f. Okay, so that's important. It has to be in the domain of f. If it's a rational function, what do we want to look out for with the domain?
Oh man, that was a long time ago.
So if it's a rational function, it's a fraction, right?
Yeah.
So if it's a fraction, yeah, we can't have zero where?
I'm about it.
We can't have zero in the denominator, okay? So if you had a value that made the denominator zero, it would not be in the domain. So basically when it says it's in the domain, it just means when you plug in that value, what's not going to happen? Okay, so the denominator equals zero would be one special case. For all the cases, you could say,
Get,
okay, so yeah, you would get out some value. It wouldn't be undefined, you wouldn't get an error, okay? So we're going to evaluate this limit if it exists. So the limit as x goes to 2. If we can do direct substitution, that means that this is in the domain and we would get a valid answer. Like we said, we have to watch out and we have to make sure that the denominator is not going to be in the denominator is not going to be 0. So if I plug in 2, okay, Megan, if I plug in 2, what am I going to get in the denominator? Okay, so tell me how you're getting it.
Because I plugged in 2 to x and then added 3.
Okay, so 2 to the 4th is going to be, it'll be 2 to the 5th. So 2 to the 4th is like 2 times 2, which is 4. 4 times 2 is,
Oh, 16.
yeah, 8, and then 8 times 2 is 16. So 16 plus 3 is going to be 19, okay? So is the denominator going to be 0? No. Is there anything else I have to watch out for with this? No, okay? So 2 is in the domain. Okay, if it is in the domain, therefore, we're going to do direct substitution. Okay, so we're going to do direct substitution, which, like I said, you guys will like this. If it's in the domain, you're just going to directly substitute 2 in for x. Can anybody tell me what the domain of this function is? How do you find the domain if it's a rational function? Yeah, you're going to set the denominator equal to 0. Okay, so if I set the denominator equal to 0 and solve, what do I get?
X equals plus or minus the fourth root of 3.
Okay, so if I set that equal to 0, I'd get negative 3, right? And then the fourth root of negative 3, can I do that? No, which means the domain is all real numbers. So really, for this function, no matter what value they gave me for x as it approaches, I would be able to find a value. So the limit here is going to be 16 over 9. Or, sorry, 16 over 19.
So if it doesn't exist, you
Yep, if it doesn't exist, you'll say that. But before we can say that, it's not just going to be if the denominator is 0, then it doesn't exist. Okay, we know that that doesn't happen even based on the first worksheet that we did, right? Remember how we plugged in 3 for 2 of those functions and we got undefined when we plugged it in? But when we looked at the table, it was actually, when we looked at the table, it was actually going towards a number. Like, do you guys remember the second one on your intro worksheet? It was getting closer and closer to what value? 6. Okay, so even though it was undefined at that value, it was getting closer and closer to 6. If you can use direct substitution, that's pretty simple. but not all limits are going to be able to be evaluated in that method. So in most situations where limits are useful, we're going to have to work a little bit harder. So the next few examples are going to show how we use algebra to find limits. Okay? And that was taken exactly from your book. So notice my proper citation. All right, for part B, we have the limit as x approaches 4, and then we have x minus 4 over x squared minus 16. Right? Now, I already tell you, it says, why can't we use direct substitution? Bruno, what do you think? Why can't we use direct substitution for this? Okay, what happens if you do plug in 4? Say it again. Okay, why not? Just be more specific. If you plug in 4, what happens? Okay, so the denominator is going to be 0, right? In fact, if you plug in 4, we'll write this to the side here. If you plug in 4, you're going to have 4 minus 4 on the top over 4 squared minus 16 on the bottom. So you'll have 0 on the top and on the bottom, which we talked about. That's called what? Indeterminate. Okay, is 4 going to be in the domain of that function? All together, please. Is 4 in that domain? No, obviously not if we're getting an error, a 0 on the bottom. Okay, so why can't we use direct substitution? Because 4 is not in the domain. Okay, does not produce a valid output. Then the next thing I asked you is, can we apply the limit of a quotient law? Why or why not? Okay, Jonathan, what do you think? Can we apply the quotient law?
I said no, because we would still get 0 over 0.
Okay, so you can't apply the quotient law, and that's because the limit of the denominator is 0. And if you look back at your limit law, it clearly states that the limit as x goes to a of g of x cannot be 0. Okay, so that means that the denominator, the limit of the denominator cannot be 0, and that's what happened. So, what should we do? Ideas? Factor. Thank you. Factor. All you negative Nellies, good goodness. I didn't say that you were kidding, I said all you negative Nellies.
Kylie said she was kidding. I was like, no, I was serious.
Okay, so what should we do? We should factor and conquer the world. Okay, so let's do it. So if we factor, do we notice a special pattern per se?
Yeah, cancel 4.
What is the pattern called?
It's a 4.
It's not called the fours?
Perfect square.
Difference of squares.
Yes, good. Difference of squares, okay? And then, yeah, you should notice, once you factor, what's going to happen?
Cancels out left with x plus 1.
Good, so you can cancel out the x minus 4 and the x minus 4. And notice that I keep writing the limit because you are taking the limit. You can't stop writing that until you're able to substitute. Okay, so factors x minus 4 cancel out to 1. Because really when you're canceling out, we have to understand that really you're dividing. Anything divided by itself is what? 1. That's why I have 1 on the top. Okay, now that I've simplified that, can I substitute 4 in and not have 0 in the denominator anymore? Okay, so then let's do that. So once you can substitute, that's what you want to do. So now I have 1 over 4 plus 4, which is going to be 1 over 8. Okay, so 1 over 8 is going to be your limit. This is something you can also check with the graph. Do you guys know what that value is as a decimal? Yeah, 0.125. So in your table, you notice it goes to 0.125. Now, when you have to solve with algebra on your quiz/test, I will make you write it as a fraction. Okay, so, and show your work. So you do have to show me that you know how to do it using the algebraic method. But that's a great way to check it. Okay, so now let's look at the next one. Okay, so this is as h goes to 0. So if I try to do direct substitution and I plug in 0, I'm going to have a problem, right? Okay, so then we have to talk about what we're going to do. So why can't you substitute?
The denominator will be 0.
Okay, yep, so 0 is not in the domain. Okay, and the denominator equals 0 when you take the limit. Okay, so that's why you can't substitute, and that's why you can't use the quotient law. Okay? Do we have any ideas on what we want to do to this one?
Take that.
Bounce back.
Could you factor?
I don't think you can factor.
I mean, like, you multiply the two things.
Yes, okay, so yeah, so you can expand this expression, right? You can multiply those two together, you can FOIL.
Whatever.
Right.
Foil. Yes.
Yes.
Foil, yes.
I want you to say the right term.
Well, I don't know why they put words with math. Like, this doesn't make sense.
They
Like,
put words with every subject.
I know, but you say, like, do the thing, and then everyone's like, yeah.
Yeah, but then how do you know if they really
George,
understand?
Everyone just trust you, okay?
Okay.
We believe in you.
No, you say what you mean what you say. Right, so we are going to simplify, so we're going to multiply the 4 plus h and the 4 plus h together, so you can do that without me, so go ahead and do that. Oh, we're actually
You got it.
this until a different day.
16 plus 8h plus h.
There is more, I
Minus
just copied the
16
wrong
over
word.
h. Ah. 8 plus h. Limit is 8 plus h.
Okay, good, so yeah, Abby, what did you notice? In the next step,
The
what happened?
16s cancel out.
Okay.
And then you can divide ah by h and h squared by h.
Okay, good. Oh, I did something that
Oh,
I'm
no.
mad at myself for. What did I do?
Should I do it too?
I forgot to write down my limit.
Oh, silly.
Okay, so
You just
limit is
add
h
it in
goes
at
to
the
0.
end.
Can't you just write like two,
Nope.
like two
Miss Whipple, you're making up
quotation
words.
marks or something?
Oh.
Miss Whipple?
That's right, that's not that.
We have to
Yeah,
do
it's
it until we
pretty
plug it in or else it's not correct. Okay, so the limit is h goes to 0. Okay, so we haven't taken the limit yet, so we have to write each time it's the limit as h goes to 0. Okay, and then, yeah, you can divide h by both of those. You can also think of it as factoring out the h, right? If you factor out the h on the top, then those will cancel. And then you'll have the limit, h goes to 0 of h plus 8, which we still can't plug the 0 in any of these steps. If I plug in 0 here, I have 0 in the denominator. Same thing with all of these. When I get to this step, can I plug in 0? Yeah, so then this will be 0 plus 8. That's when you can stop writing your limit, and then that will be your final answer. Okay, questions for me on that part? Okay, let's look at the next one, part D. So you can see, I already said, why do we need to rationalize? So let's think about this. First, if we plug in 1, what's going to happen?
0.
Yeah, the denominator is going to be 0. Okay, so we are going to rationalize, and that's because we can't do direct substitution or use the limit of a quotient law. Anybody want to tell me? Why can't we use it?
Because we still get 0 on the bottom.
Okay, so because the denominator would equal 0 as x approaches 1. Okay, so if it's going to be 0 in the denominator, you can't do direct substitution and you can't use the limit of a quotient law. Now, I told you that we needed to rationalize. Can you guys think about what that's going to look like for this one? What do you think?
Can we actually do 2 things?
Okay, what are you thinking? What are you thinking?
I thought what I did, multiply times the conjugate of the numerator.
Yes, okay, so you're going to multiply by the conjugate of the numerator in order to rationalize. So you need to multiply by the square root of x plus 1 over the square root of x plus 1. Okay, so we are going to rationalize the numerator here. Do you guys know why we don't want to multiply this by the conjugate of the denominator? What would happen if we did? What would we get? If we did multiply by x plus 1, the conjugate of the denominator. You get x squared minus 1, right? Okay, so if I multiplied by something else and then I got x squared minus 1, would that help my case at all? No, because when I plug in 1, wouldn't I still get 0? Okay, so that's why we're going to rationalize the numerator. Do we remember how to rationalize the numerator? Okay, yeah, do you guys remember how to multiply? Root x times root x is what? Okay, good. In the middle and on the outside, those two values are going to cancel. Negative root x plus root x. Negative 1 times 1 is? Yep. Okay, now, look, I have x minus 1 on the top. I'm multiplying these together. I'm going to leave it as x minus 1 times the square root of x plus 1. Why would I do that? Okay, they're going to cancel. Okay, how would you know not to do that? Well, you should recognize that once you get the numerator. Once you get the numerator, you'll say, oh, those are the same factor. If they're the same factor, okay, then they are going to be able to cancel out. And again, write your limit. Okay, so the limit, as x goes to 1, these would cancel. So you'd have 1 over the square root of x plus 1. Okay, so the x minus 1 factors cancel. Okay, now can I plug in negative 1 here and get a valid answer? Okay, so if I plug in 1, I would have 1 over the square root of 1 plus 1. What's the square root of 1? 1. So 1 plus 1 is going to be 2, so 1 half. Bless you. Okay, good. Now, I need you, well, first you have questions on this? Yeah, Matt.
If we forget the limit on like a test, but we put in our answer, would you mark us wrong?
If you forget it for every single time, yes, they will.
Okay. If we get it for once or twice.
Twice.
How about 3 times?
No.
What about once?
Maybe once I'll be forgiving.
What about 20?
But if you keep doing it with all of them, you won't.
Or if you just
But that's also something that we're going to practice a lot with the next couple sections. Okay, so I made a mistake and copied the wrong page here, so we're just going to go to the back. Okay, this is for another lesson. Not today, so no graphing today, yay. Okay, so on the, you will want to continue it on the back, but it is going to be part E. Okay, so for part E, Okay, yep, so go to the back.
Trying to disable me in class?
So this is the limit as t goes to 0 of the absolute value of t. So that's given to you. Okay? No. Okay, so the limit of the absolute value of t as t goes to 0. Okay, so remember, because of the absolute value, you're going to have the following situation. And we'll just write that out. Okay, so remember, because of the absolute value, we have the following situation. Okay, so with an absolute value, do you guys remember what the graph of that looks like? It does. It looks like a V. Okay, we'll talk about that in a moment. We can write the absolute value as a piecewise function because one piece of it, if your t value is positive, okay, when you plug that in, you're just going to get t. It would just be the normal t value. But you can also plug in negative t. So if t is less than 0, okay, what you would be plugging in is a negative t value, negative t. So on one side, it's going to represent the positive values, which are going to be from the right side of the graph. On the other side are going to be the negative values, and those are going to be the left side of the graph. Okay. I also think it helps for reference if you know what it looks like, and we'll kind of use that in the next one as well. So because you have these two different values, what we have to do, so we have to evaluate each side. Okay, so we are going to evaluate each side. If the limits on both sides are the same, the limit is equal to that number. Okay, so it's whatever number you're approaching. Okay? So similar to like we did yesterday. Remember yesterday we were approaching limits from two sides, and on one side it went to 4, and then on the other side it went to 4. So the limit of the two-sided function was what? If the left goes to 4 and the right goes to 4, the two-sided limit is 4. Okay? What if they go to two different values? It does not exist. Okay? So if the limits are not the same, then the limit does not exist. See, don't you guys appreciate now how much I type out for you?
Oh, yeah.
Okay, so just again, if the limits on both sides are the same, the limit is equal to that number. If the limits are not the same, then the limit does not exist. Okay, and like we talked about before, if you are graphing this, I think it is going to be helpful to just have a quick visual representation. If you plug in 0, you get 0. If you plug in 1, you get 1. If you plug in negative 1, what do you get? 1. You plug in negative 2, you get 2. If you plug in positive 2, you get 2. Okay, so that's why it creates the V shape, okay, on both sides. So we're going to use that to help us evaluate each limit. So the first thing we're going to do is evaluate from the right. So we're going to find the limit as t approaches 0 from the right, absolute value of t. Okay, so if you're looking at that from the right side, if we're thinking of this algebraically, this would be the same thing as the limit of t approaches 0 from the right of t. Okay, so on the right side, we have the positive values, right? On the right side of the graph, we have the positive values for t. So if I plug in 0, then really this limit here is just going to be 0. So just like we were doing before, you're still going to substitute in that value. Okay, and then we'll do the limit of the left side. So the limit as t approaches 0 from the left of the absolute value is the limit as t approaches 0 from the left of negative t. Okay, so on the left side, the value of t is negative. So really I'd have negative 0, which there is no positive or negative for 0, so it is still just 0. So if both of these limits are 0, then what is our limit going to be? 0. So therefore, the limit as t goes to 0 for the absolute value of t is equal to 0. Okay, so you're showing me both sides, and then if they're the same, then the limit is going to exist, and it'll be that number. In this case, it was 0. Okay? Now, Ms. Whipple, thank you for making sure I completely understand this concept before I have to do it by myself. Okay, so now we're going to do the limit as z goes to 0.
Why are there different letters?
Yeah, Ms. Can we, actually, I have a petition against T, because like whenever you're doing T, it looks like a plus sign.
So you have to
That's
make
why.
it cursive.
That's why I curve mine.
Yeah.
Yeah, and like with the z.
I don't write them like that in other.
Yeah.
Yeah, whoa, 2 plus Z is.
That's what
Why are
it
you
is.
writing this so
Let's not discriminate against letters.
Why can't we just stick with X?
Yeah, whoa.
X is
Because
multiplying.
life is full
yeah,
of
but that's
things
what
more
we're
than
Yeah, but then
Yeah.
you
Who writes
yeah.
X
Yeah.
as multiplying?
You're gonna have different
Okay, I know
variables
what
in
you
your
mean. It's so
homework,
hard
so
to
we're gonna have different variables now.
For what?
Okay, so for the first one, I wrote out the piecewise for you so you could see why we're doing the t and the negative t. Really, you guys can just jump into finding each limit. Okay, so if you have the absolute value, that means you have to find the limit from the left and from the right. Now, the reason I usually start with the right is because that's a little bit easier to do. So I can find the limit as z approaches 0 from the right, and if it's from the right, it's going to be the positive values. Okay, so if it's the positive values, we're going to write this out original first. Okay, if it's positive, just like we had before, if it was positive, we would just use t. This is positive, so we're still just going to have 2 plus z, and that's going to be over 2 plus z. Now, can I substitute in 0 for these? Yes, okay, so that's what I'm going to do. So I'll have 2 plus 0 over 2 plus 0, which will be 2 over 2, which will be 1. Okay, so as you're looking at this limit, as it approaches 0 from the right side, you're going towards 1. Now we're going to do the left side. strong side. So the limit, as it comes from the left, what did we put in front of the t last time? Yeah, a negative value. So this one's a little bit different because before we just had one term, now we have two terms. If you have two terms, you're just going to put the negative in front. Okay, so this is going to be the limit as z goes to 0 from the left of negative 2 plus z over 2 plus z. So the negative is just on the top because that's just the part where the absolute value is. And then we are going to substitute in 0. So this will be negative 2 plus 0 over 2 plus 0. So on the top we'll have negative 2 over 2, which will be negative 1. What's that? Not necessarily. So it does depend on your values. So because one is 1 and one is negative 1, what do we say about our limit? Okay, so this original limit does not exist. Right? Because the left and right limits are different. Okay, and then you guys are going to do 13.2, numbers 5 through 7, 11 through 18,